3, 2, 1. Dr. Peyam in the house.
Yeah! Alright, thanks for watching. And today I want to give you a counterexample to the celebrated Fubini theorem, which tells you that given a function, you can calculate the double integral by first integrating with respect to x and then integrating the result with respect to y and vice versa. So f of xy dy dx. So Fubini says, if it's true, it says you can literally interchange x and dx and dy. But today I want to give you an example where this is not true. And for this, it's very important, I think, to always check for the assumptions of Fubini's theorem. Of course, in multivariable calculus, everything is smooth and integrable, and we don't really care about that. But in general, you have to watch out for stuff. And in particular, consider the following function. So R, first of all, is the rectangle 0, 2 cross 0, 1. So x is between 0 and 2, and y is between 0 and 1. And f of x is the following function. It's xy, x squared minus y squared over x squared plus y squared cubed. And notice this is undefined at 0, 0, and in particular to define it at 0, 0, you define it to be 0. And I'll talk about the assumptions in a second, but first of all, I forgot to mention, this is not my example. I found it some website of Johns Hopkins University, and I still think it's too cool not to teach. So take this function, and let's evaluate both of those integrals really carefully. So the first step is to integrate in the y direction. So step 1. And let me explain what I mean. So you have again your xyz plane, z-plane, and then we have x between 0 and 2, y between 0 and 1. So this is our rectangle. And this is R. And you have this function floating around. I don't know what it looks like, but let's just assume it's some surface here. Might be a very wrong picture. And what we would like to do, we would like to, let's say, integrate in the y direction, which means that for every x, let's see, I always get those confused. So for every x, we want to calculate, the a of x. So I guess we first integrate in the x direction. So for every x, consider the horizontal slice, which I like to call a of x. So we want to consider those slices, a of x, and then what we're going to do, we're going to slice a of x in the x direction to hopefully get the whole volume under the curve. So again, this is a of x, a of x. So in other words, a of x is the integral with respect to y of your function f, and then we integrate this with respect to x. So, let's see. So again, a of x becomes, in this case, the integral from 0 to 1 of f of xy dy, which becomes the integral from 0 to 1 of xy, x squared minus y squared, over x squared plus y squared cubed dy. And notice here we have a y which looks like a derivative of y squared. So it might be good to use a substitution x squared plus y squared, because at least it simplifies the denominator. So u is x squared plus y squared. And so du, again you want to do it with respect to y. So du over dy dy, which just becomes 2y dy. And that's good because we have a y dy here, so that's good. And then, so y dy equals to 1/2 du. And now we would like to do the endpoints. So the endpoint corresponds to y equals to 0. So u of 0 becomes x squared, and u of 1 is x squared plus 1. And lastly, what about our function x squared minus y squared? Let's see what that looks like. So x squared minus y squared equals to x squared minus, so y squared is u minus x squared, so u minus x squared, and that just becomes 2x squared minus u. Okay, we have all the ingredients that we need, so this integral becomes integral over our new endpoints, x squared and x squared plus 1. This x stays as it is. X squared minus y squared becomes 2x squared minus u. The denominator becomes u cubed. So that all this work just to simplify this to u cubed, okay? And then 1/2 du. And this is very nice because essentially this almost just becomes a power function, because remember x is constant here. So we do that, and then this simplifies to the following. That equals to integral x squared to x squared plus 1, x cubed over u cubed minus x over 2u squared du. Just split up the fraction, and then you just calculate this. So again, x cubed is a constant, and then antiderivative of u to the minus 3, it's minus 1/2 u to the minus 2, so minus x cubed over 2u squared, and then plus x over 2u. Because an antiderivative of minus 1 over u squared is 1 over u. And remember, you evaluate this from u equals to x squared to u equals to x squared plus 1. I was like, why is this so complicated? Okay, minus x cubed over 2, x squared plus 1 squared, plus x over 2, x squared plus 1, plus x cubed over 2, x squared squared, minus x over 2x squared.
Yep.
And here's the nice thing. This simplifies, so this is 1 over 2x. This becomes x cubed over 2x to the 4th, so 1 over 2x. This cancels out. And then this, you just put it on a common denominator, so it's minus x cubed plus x times x squared plus 1 over 2 times x squared plus 1. And see how nice this is. This becomes minus x cubed plus x cubed plus x. This cancels out, and we get x over, sorry, this is a square, x over 2, x squared plus 1 squared. And I did this on my first try. Okay, so what have we found? We found that the slices a of x equals to that. So just let me use this one. Okay, so we found that a of x equals to x over 2 x squared plus 1 squared. And I like to remind you that f of xy equals to xy over x squared minus y squared over x squared plus y squared cubed. Because there's one little technicality I didn't really look out for, but it's possible that x equals to 0. And so in our calculation, it's possible that this thing doesn't quite work. But the nice thing is, look, if x equals to 0, then this function f of x is always 0. So f of 0y, if you plug in 0, you always get 0. And in particular, even in that case, well, the slice should be 0, right? A of 0, that would be the integral from 0 to 1, f of 0y dy. Well, that should be 0. And here's the cool thing. If you plug in x equals to 0 in this formula, we get 0 over 2 times x squared plus 1. I guess 0 squared plus 1. And it still becomes 0. So the point is this formula is also valid for x equals to 0. So it's valid for all x in our domain. All right, that's good. And now the next step is we want to integrate this. So let's do the integral from 0 to 2, a of x dx. Well, that's the integral from 0 to 2 of x over 2, x squared plus 1 squared dx. And this looks horrible, but if you want, you can just use a u substitution. U equals to x squared plus 1, and you find an antiderivative. It's minus 1 over 4. X squared plus 1 squared, no, just this, from 0 to 2, and that becomes minus 1 over 20 plus 1 over 4. So, on the one hand, what we found, if we take the slices in the x direction and we integrate that, by the way, this is, okay. So in other words, if we take, we have this function here. So we had our slices, so I guess that should be dx, okay. We had our slices a of x. Okay. And we integrate that in the x direction, then the answer should be 1/5. In other words, in the Fubini's theorem, it would say that the volume under the function, the volume under the surface, should be 1/5. And now let's see what happens in the other case. What if we take the slices, in this case, in the horizontal direction, and sum them up? So I guess this should be step 2. Let me use it here. All right, número 2. C. Step 2. In this case, what we want to do, we want to do the other case. So again, you have your rectangle here. Again, so y is from 0 to 2. And then y is from 0 to 1. X is from 0 to 2. And this time we would like to take the other slices. I don't know if I should call it vertical or horizontal, but slices in this direction. Let's call it b of y. And we want to integrate with respect to y. So, what is b of y? In this case, it's just the integral of the function with respect to x. So, b of y equals to integral from 0 to 2 of f of xy, let's say dx, because in the end we want a function of y, and so this becomes integral from 0 to 2 of xy over x squared minus y squared over x squared plus y squared cubed. And again, ideally we would like to get rid of that denominator. So in this case, let u be x squared plus y squared. Except in this case, we integrate with respect to x. So we do du dx. So du equals to du over dx. That becomes 2x dx. And then, again, u of 0. In this case, x equals to 0. That becomes y squared. U of 2 equals to y squared plus 2 plus 4. Okay, so x squared, so we want now x squared minus y squared. Before we solve this in terms of x, but now we want to solve this in terms of y, because we want by, and so x squared becomes u minus y squared, so u minus 2y squared. And so in the end, this integral becomes integral from y squared to y squared plus 4 of, so 2x dx is du, x dx is 1/2 du, so 1/2 y times u minus 2y squared over u cubed, and then du. And then essentially you just solve it the same way, so this becomes, let's see, integral from y squared to y squared plus 4 of y over 2u squared minus y cubed over 2u cubed du. You find an antiderivative, so minus y over 2u plus y cubed over 2u squared, and then u goes from y squared to u equals to 4 plus y squared, and then you evaluate that, then you get okay, minus, sorry, that's the plus, okay, so minus, let's see, y over 2 times 4 plus y squared plus y cubed over 2 times 4 plus y squared squared plus, let's see, y over 2 y squared minus y cubed over 2y to the 4th, and just as last time, this becomes 1 over 2y, this becomes minus 1 over 2y, this cancels out, and then you put it on the common denominator, just as last time, and you get minus 2y over 4 plus y squared squared.
Whoa.
So it gets messy. This is b of y. Last thing is we have to, I know, I'm exhausted. Last thing is we have to evaluate that. I know, almost there. But the point is it's similar, but not quite the same. And again, notice how much work we have to do to show it's wrong, okay? Which means it's a very powerful theorem, okay? So it's hard to disprove it's wrong. So, and then also, by the way, that formula is true for y equals to 0, yada, yada, yada. And now let's calculate the integral from 0 to 1 of dy dy. That's integral from 0 to 1 of minus 2y over 4 plus y squared squared dy. Then u is 4 plus y squared. And then if you do that, you get 1 over 4 plus y squared from 0 to 1, which becomes 1/5 minus 1/4. And that's minus 1 over 20. Oh no. So yeah, minus 1 over 20, which is kind of weird. Because look, we had the same function, right? Like this was f. On the one hand, if you sliced it horizontally like that with a of x, if you sliced it like that and you got this, then the answer for the volume, what was it? Was 1/5. On the other hand, if you slice it like that, and you do it like this, with dy, again, there are two kinds of people in this world. The ax people or the dy people. Which one are you? Figure that out. Then you get the answer is minus 1 over 20. On the other hand, you know, they should all calculate the same thing. So the question is, what is right, what is wrong? Well, basically, in this thing, Fubini's theorem doesn't work. And by the way, I think, let's see, okay, never mind. I thought f was positive or something, so there's a correct answer, but no, here, maybe the answer is neither of them. But what happened here, because, remember, f of xy was xy over x squared minus y squared over x squared plus y squared cubed. The problem is this function, the reason Fubini's theorem doesn't apply is that the function itself is not integrable. In other words, if you take the double integral of f of xy dx dy over the rectangle, then you should get infinity. I guess absolute value of that. You should get infinity. And the clue is, notice basically, the problem is, at least in calculus, we usually integrate continuous functions. This function is not continuous. It blows up at 0, 0. And in fact, it's not even Lebesgue integrable because essentially it blows up pretty badly. And for example, notice the following. The reason it blows up because notice it takes, arbitrarily large positive and negative values near the origin. For example, you can calculate that f of 2t, t is 6 over 125 t squared, and f of t 2t. So in other words, I think if you go through the line, x equals to 2y, so y equals to x over 2, it blows up in this direction. Sorry, the t squared is there. So along this line, the function blows up like x squared. Along this line, the function is even negative. It blows up at minus 6 over 125 t squared. I think it's a time for me to stop, but there's one little remark. Whew. Perfect. Alright, so we've seen that on this line y equals to x over 2. It's very positive and blows up to infinity. This function on the line y equals to 2x, it blows up to minus infinity. So it goes very down, and in particular this function is very ill-behaved and it's very non-integrable, and in fact it sort of behaves like the function 1 over t squared, and that function is not Lebesgue integrable because the integral is infinity. So really what you have to check for Fubini's theorem, you have to check not only that the function is integrable, but also any slice you calculate, the slice itself has to be integrable, and I guess at least measurable, and the integral of each slice has to be integrable. So it's really a very picky theorem, but once you check the conditions, which is usually not hard to check, then you can apply Fubini's theorem. And of course in calculus you don't care, right? You just apply it.
Yeah.
Alright, so if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.
Nice.
Woohoo!